everyone. This is the Physics 110 GR archive for GR2D. I'll be going through workout 2 in this video, all 4 parts. So in this question, we have a block that's initially compressed by a spring. It's released from rest, goes up a hill, hits a frictional patch, and then ends at the point T. So it's a huge conservation of energy problem. And we'll start with part A. Calculate the potential energy at the following points, point Q and point T. So if we're looking at point Q and point T, good thing about point Q, the spring is no longer being, the block is no longer being compressed by the spring at point Q. So at point Q, the only potential energy we have is gravitational. Well, we are told that assume zero gravitational potential energy at ground level. So our only potential is due to gravity, which is mgh. That's 12 times 9.8, and our height is 0 because it's on the ground level. So our potential energy is 0 joules at point Q. At point T, do the same thing. We only have gravitational potential energy at that point. The spring only gives potential energy when it's actively being compressed. That it doesn't carry on throughout the whole time. It's just while it's being compressed. So we only have to look at gravitational again. We're going to do 12 times 9.8. At this point, we are at height h2, which given to us is 13 meters. Okay, so at point T, we're going to calculator, 12 times 9.8 times 13, we get 1528.8 joules. So that one, not too hard, just plug and chug, and realizing that at point Q, this block is no longer being compressed by the spring, so it does not have any spring potential energy at that point. So that might trip you up, but it's not a trick question, it is actually 0. Question B, determine the block speed at point T. Okay, so now we're looking here, we want V final at point T. Okay, so the good thing about energy equations is you can pick your initial and final from wherever you want. So if I take in all the givens that I have in my problem, I can see that the problem is giving me a velocity at point S. And so I want to use that one because I can figure out the kinetic energy there and the potential energy there, and then that's the closest point to my final, and we can just do a simple conservation of energy from there and figure out the speed. So initial potential plus initial kinetic equals final potential plus final kinetic, block speed at point T. So if I'm picking S as my starting point, the potential energy there is mgh, and K initial is going to just be the 1/2 mv squared because the block is moving at that point. U final, I'm going to have, since at point T we're still at an h2, there is going to be a height there, so we do have gravitational potential, and we're moving at some speed, which is what we're trying to find. Some of you might be wondering why we don't put our initial point over here at point P with the spring. Well, the reason is if we were to use that as our initial point, we would have to take into account spring potential energy. And if we did that, we would have a 1/2 kx squared. Well, we haven't calculated k yet. That's actually in part C. So we don't want to use that as our initial point because then we'll have too many unknowns. We would have an unknown k in there that we would only have one equation, and you can't use one equation to find 2 unknowns. So it's easier to just use what you're given, start it at point C, and use that. That's the same reason for those of you who are then like, oh, well then why wouldn't we pick point Q? Because then that wouldn't have spring potential energy. We also don't know the speed at point Q because it didn't tell us the speed coming off of the spring. It just gave us the distance we compressed the spring, and so we would have had to do another calculation to figure out this initial, which again wouldn't help us in finding our final velocity. So that's ultimately why we pick point S as our initial point. So just plugging in numbers. Before I do that, for those of you that don't want to plug in as many numbers into your calculator, if you can recognize that you have a mass in all of your terms, you can cancel that out. For those of you that want to just plug in all the numbers and put them all into your calculator, go for it. But I'm just going to say, okay, there's a mass in all of these. So if I were to divide both sides by mass, or in this case 12 kilograms, the mass would go away in all of these terms. So I'm just going to copy down everything but the mass. So gravity, 9.8 meters per second squared. My height at point S is h1, which is 15 meters. My kinetic energy, I have 1/2 v squared. This is the v at point S, which it gives it to us, 13.6 meters per second. I'm going to square that term. And then I have a 9.8 meters per second squared again. My height at point T is now h2, which is 13 meters. And I'm going to add that to 1/2 v final squared. And v final squared is what we're trying to find, and that's our only unknown in this equation, so we know we can solve for that. So now I'm going to put all this into my calculator. I'm going to leave this step so I don't mess up. So I'm going to go 9.8 times 15 plus 0.5 times 13.6 squared. And I'm going to subtract 9.8 times 13. I get 112.08. Multiply that by 2. And take the square root of it. And our V final is 14.97 meters per second. So that's the velocity at point T. Okay, moving along to part C, determine the spring constant K. So now we need to look at point P. Because we're going to use this as our initial, to calculate our initial potential energy. And then we need to pick a final point. At this point, now that we've solved for the final velocity at T, you could use that. But be careful in these free responses about using things that you've calculated in previous problems. If there's an easier option with something that the problem has given you, I would go with that one, because then if we happen to make a mistake in part B and got a wrong velocity, then we wouldn't be reusing that in part C and possibly getting more points off for using a wrong number. They try not to do double jeopardy, to where if you got something wrong for point B and then used it, they wouldn't take off more points. But just in case, let's use something that they gave us. So we know they gave us the speed at point R. And so we have all our givens for potential energy and kinetic energy at point R. That could be our final. And then we don't know the potential energy at point P, and that's what we're going to try to find to get our spring constant K. So I'm going to write all this out again. I'm going to do potential energy, kinetic energy equals final potential plus final kinetic. So in this case, we have two forms of potential energy to look at. We have our gravitational and spring potential. Gravitational, luckily this block starts on the ground level, so we don't have any gravitational, but we do have spring potential energy, which is 1/2 kx squared. Our initial K, let's say, the problem says that the block is released from rest. So that means we don't have any K initial. So I'm going to get rid of that plus sign. Okay. My U final. So at point R, that's what we're picking as our final. The only potential energy we have is gravitational, and it's at height 15. So I'm going to do that as an mgh. And we also have a final kinetic, because it's moving at that point. Okay, so now we're going to plug in some numbers. 1/2, we don't know our K, but our X, the problem said it was compressed 2 meters. We have our mass of 12 kilograms. We have gravity. And we have a height of 15 meters. Okay, now for our kinetic, we have 1/2 mass, 12 kilograms, times v squared. Our velocity at point R is given as 15 meters per second. and that's going to be squared. Okay, so again, we have a ton of numbers and just one unknown, so we can solve for k. So I get 12 times 9.8 times 15 plus 0.5 times 12 times 15 squared. I'm going to multiply by 2 to get rid of that 1/2. Whoops. 3, 4. Multiply by 2 to get rid of that 1/2. And then I'm going to divide by 4 to get rid of that 2 squared. And after all the calculations, I get 1557. And K is measured in Newton meters. Okay, that's our K. Last time, we're at D. Determine the coefficient of kinetic friction. Okay, so now we're only focusing on this frictional part. So, when you're thinking about friction, you should be thinking about forces of friction and therefore work done by friction. Because we know the velocity at point R and point S, which means we can find kinetic energies at at those points, which means we can use the work kinetic energy theorem. So the work done by friction is going to be the change in kinetic energy over the frictional area. So let's see here. So we know that, I'm going to call this force due to friction, and I'm going to say, we know that the force of friction is always the coefficient of friction times whatever our normal force is. And then we also know that work done by friction, work is just force times distance, so it's going to be the force of friction times d, or if we substitute in our force of friction, that's our coefficient times our normal force times the distance we traveled over that frictional surface. Okay. So now using work kinetic energy theorem, we know that work is change in K, or work is K final minus K initial. So we can plug a bunch of stuff in now. We can say that work is our coefficient of kinetic friction times our normal force. In this case, the block is on a surface with a weight going down and nothing else acting on it in the vertical direction. So the normal force is just the opposite of the weight. So it's going to be mg. And then our distance d, traveled along friction. So that's our work, and that's going to be our K final. So 1/2 mv squared minus our K initial. And be careful, we're looking at kinetic energies. Our initial and final is at point R and point S. The initial and final of the work done by friction. So now we're going to plug in all these numbers, and hopefully we only get one unknown. So our unknown right now is our kinetic friction. Our mass, again, we can cancel out our mass in all of these. This time I'm going to write it out. 12 kilograms times 9.8 meters per second squared. And our d, distance traveled over the frictional surface, is given to us as 9 meters. We have 1/2 times 12 kilograms times v final squared. So v final is the velocity at point S, which was 13 meters per second, and we're going to square that. And then our initial kinetic energy was 1/2 times 12 kilograms times our initial velocity at point R, which was 15 meters per second squared. Okay, so we have all these numbers, one unknown, bunch of plug and chug now. So I'm going to do 0.5 times 12 times 13.6 squared minus 0.5 times 12 times 15 squared. I'm going to divide by 12, then divide by 9.8, and then divide by 9. And I should get a coefficient that equals 0.227. And since it's a coefficient, you can ignore a negative sign. For me, I got a negative sign. It's just because we're losing energy And so when it's K final minus K initial, you're going to get a negative number. It's like taking the absolute value of that, because the coefficient of kinetic friction is always going to be positive. So we get 0.227. So that concludes the whole workout 2.